Welcome to the course on an introduction to coding theory. I am Adrish Banerjee from IIT Kanpur. In today's lecture, we are going to talk about distance properties of turbo codes. So this is the outline of today's talk. We'll first give an example of a weight distribution of convolutional code, and we will compare it with a weight distribution of a concatenated code, and we will see what effect does interleaver has on the weight distribution of the concatenated code. Then we will introduce this concept of spectral thinning, which is visible in turbo codes if we use feedback encoders. And finally, we will show how we can make use of this concept of uniform interleaver to derive expression for average weight enumerating function of turbo codes. So as we know, turbo codes have very good performance at low signal to noise ratio and at moderate BER, and this is due to its random like weight distribution which is produced when we consider pseudo random interleavers combined with systematic feedback encoders. If you recall, a turbo code is a parallel concatenation of two constituent encoders. So this is the encoder 1, encoder 2, information bit enters encoder 1 and the interleaved version of the information enters encoder 2. These are the parity sequence coming out of first encoder and second encoder, and then this is systematic. So typically you have, this is the example of a rate 1/3 parallel concatenated code. Now we'll try to see, as I said, we'll try to look at the distance spectrum of a concatenated code and see how is it different from a convolutional code. So let us start with an example. So we are considering a rate 1/2 convolutional code with memory 4 whose generator matrix is given by this. So this is a feed forward encoder. Now this code has a feed distance of 6, which is obtained when we feed an information sequence of the form UD equal to 1 plus D. So this is of the form input sequence 1 1 and all zeros. Now you already know how to find a D free of a convolutional code. Given a generator matrix, you first have to find out its state diagram, then you draw its modified state diagram, and from there you can calculate weight enumerating function, input output weight enumerating function, so conditional weight enumerating function. So all those things we have already discussed in our earlier lecture. So you know how, given a generator matrix, how to find out the weight distribution of a convolutional code. Now let us consider an equivalent convolutional encoder whose generator matrix is given by this. Now note, this is equivalent to this feed forward generator matrix. So this is a feedback encoder and this is a systematic encoder. Now in this case of the systematic feedback encoder, the minimum weight code word is again 6, and which is produced by an input of the form 1 plus D5. So this is 1 0 0 0 0 1. So this is 1 D squared D cube D4 D5. So this is produced by a sequence of this form. Now since these two generator matrices are equivalent, so they will produce the same set of code words. The only difference is the mapping between the information sequence and code word will be different. Now let us consider a terminated convolutional code. So let's say our overall information block size we want is n. So in this example, since the memory here is 4, you can see this is memory is 4 Okay, this is a rate 1/2 memory 4 code. So if we want to terminate this encoder, we would require 4 termination bits. So let us consider an information block of length n minus 4, and to this we will add 4 termination bits. So the overall code word length will be, because it's a rate half code, overall length of the code word would be 2 times n. So this is information sequence n minus 4, and plus we add 4 tail bits, that is n, and since the rate half code, so the number of coded bits that we will get is 2n. So this will result in a 2n n minus 4 block code. So this is roughly a rate half code if n is very large. Now please note that the termination bit depends on the type of the encoder that we are using. So the termination bits that we will use for the feedback encoders are different from the termination bits that we will be using for a feed forward encoder. So in this I have drawn, so consider n equal to 16. So this is a 12, 32. So n is 32 and k is 12 here. Remember, we were using a generator matrix of memory order 4. So we were terminating it. So 4 were tail bits. So this is a 3212 terminated convolutional code. And look at the weight spectrum of that. So there is a code word or 0 code word. Then we have 11 code words of weight 6, 12 code words of weight 7, 23 code words of weight 8, 38 code words of weight 9, and so on. Now let us compare the weight distribution of a terminated convolutional code with a corresponding parallel concatenated code with similar parameters. So the thing to be noted here is, if you look here, the multiplicity of code words having small weight is quite high. There are 11 code words of weight 6, 12 code words of weight 7, 23 code words of weight 8, 38 code words of weight 9. So the statement which I am making is the weight spectrum of terminated convolutional code is dense at low weight. Now if we have a convolutional code which has 80 code words of weight d caused by a set of information sequence starting at time 0, then it also has these 80 code words of weight d caused by a set of information sequence of the form dud at time 1, or 80 code words of weight d caused by the information sequence of the form d square ud starting at time d, and so on. So this time invariant property of convolution encoder accounts for the relatively large number of low weight code words in the weight spectrum of the convolutional code. Now let us now consider the equivalent systematic feedback encoder. The same, this is equivalent to the feed forward encoder generator matrix that we saw earlier. Now we want to construct a parallel concatenation of 2 encoders which has the same parameters as the terminated convolutional code that we had. So how do we get it? So as you recall, turbo code is of the form like this. So this is encoder 1, this is your encoder 2, and then this is your interleaver, and then you have parity stream coming from encoder 1, parity stream coming from encoder 2, and then you have these systematic bits, right? So if you have k information bits coming in, here you are getting k information bits, here you are getting n minus k, parity bits. Here you're getting n minus k parity bits. Now let us consider an input of length 16 where 12 of them will be information bits, okay, and 4 of them will be tail bits, which we use to terminate this convolutional encoder. So we are considering an input of size 16, 12 of them is information sequence and 4 are these tail bits which are used to terminate this convolutional encoder. So this we are feeding to our encoder 1, which is this encoder E1. Okay. Now input sequence, so we are feeding an input sequence, and remember this is our rate 1/2 code, because this is a rate 1/2 code. So if we feed a sequence of input bit 16, the parity bit that will come out will have parity bit of length 16, because here k is half of n. So if we feed in an information sequence of length 16, here we are getting also a parity sequence of length 16, because it is a rate half code. Next what is happening is, so this information sequence is interleaved and fed to this second encoder. So what the second encoder gets is an interleaved version. Interleaved is nothing but a permuted version of this information sequence. So this is a length 16 sequence that comes here, and this also generates a parity sequence of length 16. So we need to specify, remember we are trying to get to the distance profile of a parallel concatenated code, and the distance profile of parallel concatenated code depends on what type of interleaver we are using. So in this particular example we are specifying one such interleaver pattern. So you can see here I have specified here. So 0 here means the first bit stays here in the interleaved version. In the interleaved version the first bit belongs, second bit belongs to the input U8 and like that. So U0s are the original input sequence and UI hats are the interleaved information sequence. So this is the interleaving pattern I am using for this particular example to derive the weight distribution of this parallel concatenated code. Now this interleaved information sequence is fed to the second constituent encoder, and which produces a new set of parity sequences. Now as you know, the parallel concatenated code that we drew is actually a example of a rate 1/3 code. This was our parallel concatenated code. Our objective is to first compare the weight spectrum of convolutional code to that of a turbo code, and the convolutional code that we studied was a rate half code, but this is a rate 1/3 code. So what do we need to do to make it a rate 1/2? So we are going to puncture the parity bits. So we are going to send alternatively parity bits from output of a first encoder or output of the second encoder. So for example, let's call this V0, V1 and V2. So what we are going to do is, at a particular time instance we will transmit V0 and V1 and would not transmit this parity bit, and the second instance we will transmit this information sequence. We would not send this parity bit, but we will send parity bit from this encoder. So we need to puncture every other parity bit in each of these streams to make it a rate 1/2, and we denote a puncturing pattern like this. So you can view this as, so if there is a 0 we are not transmitting that bit, if there is a 1 we are transmitting this bit. So you can view this as like this. At odd time instances I am sending parity bit from the second encoder, whereas in the even time instances I am sending parity bit from the first encoder. So this will make the overall rate of this parallel concatenated code as rate half, which is same as the original convolutional code that we were talking about. Now look at the weight distribution of this 3212 parallel concatenate code which we just talked about. Now note, in case of convolutional code, the minimum D free was 6, but here we see there is a code word of weight 5. However, the point to be noted is this. Now let's look at the multiplicity of code words of low weight. In case of the example that we considered earlier of the terminated convolutional code, in that case we had 11 code words of weight 6, whereas here we are having only 4. We were having 12 code words of weight 7 for the convolutional code, here we are having 8. We were having 23 code words of weight 8, here we are having 16. We were having 38 code words of weight 9, here we are having 30. So note that in case of this concatenated code, we are noticing that as a result of this interleaver, the multiplicity of low weight code word is reduced. Now we considered a very simple example with interleaver size of just 16. Now if we increase this interleaver size, this effect is even more pronounced, and this is what we call spectral thinning. So parallel concatenated code has a spectrum which is not as dense as convolutional code. In fact, we note even with a very small example where we considered an interleaver size of 16, we saw that low weight code words, the number of low weight code words, the multiplicity of low weight code words have reduced in case of turbo codes. Now this effect of parallel concatenation, where the multiplicity of low weight code words getting reduced, is known as spectral thinning, and this is observed when we are using systematic feedback encoders in convolutional codes as consistent encoders. Now the interleaver causes most of the low weight parity sequence from the first encoder to be able to match to the high weight parity sequence from the second encoder. So the idea of design of interleaver is such that if the parity sequence coming out of the first encoder has small weight, then the interleave sequence, when it's entering the second encoder, it should produce a larger weight sequence, so that overall code weight sequence is good. Now we just showed the effect of spectral thinning with the help of a very small interleaver size of 16. Now this effect is more pronounced if we take larger interlevers. So let's say if I take interleaver size of 100, 1000, 10,000, you will see a much pronounced effect of this spectral thinning. Now different interlevers and puncturing pattern would give different weight spectrum, but this result is very typical of turbo codes. Now spectral thinning has very little effect on minimum distance of the turbo code. However, it greatly reduces the multiplicity of low weight code words. In the example that we considered, we saw that the minimum distance was 5, whereas for the convolutional code it was 6, but we only had one code word of weight 5, whereas if you look at code words, a number of code words of weight 6, 7, 8, 9, it was reduced in the case of parallel concatenated code. So as the block size increases, as the interleaver size increases, the weight spectrum of turbo code looks more like a random distribution. So it's like the weight distribution as if every bit of a code word was randomly selected according to some IID distribution. Now the example that we took, we had considered a feedback systematic encoder. Now if we replace that feedback encoder with a feed forward encoder, we see a very small spectral thinning effect even with large block sizes. So, this spectral thinning effect is pronounced in case of a recursive encoder, not in the case of non-recursive encoder. Now, we can explain why feedback encoders are better. If you feed in a weight 1 sequence to this feedback encoders, they would not get terminated, so they will result in large weight output sequences, whereas if we feed a weight 1 sequence to a feed forward encoder, it can get terminated and we may get lower weight sequences. So, the response to a single input 1 in case of a feed forward encoder is localized, whereas for a feed back encoder it extends over this entire block size. Now, this property of feedback encoders is exploited by the pseudo-random interleaver to produce this spectral thinning effect. So, what we have done so far is we have with the help of a simple example of a 3212 terminated convolutional code and in 3212 turbo codes, we have shown the effect of spectral thinning. Now we want to find out how can we find out the weight distribution of a parallel concatenated code. So again we will take a very simple example, and with the help of this example we will try to illustrate how we can compute a weight distribution of a parallel concatenated code. Now, as you can understand, the exact weight spectrum of a turbo code depends on a particular interleaver. So, the weight spectrum is dependent on the interleaver that we are using. So, we are going to make use of a device, we call it uniform interleaver. So, this will help us come up with the weight enumerating function of this parallel concatenated code average over all interleaver. So, what is a uniform interleaver? A uniform interleaver of length n is a probabilistic device which maps an input block of weight w into all distinct nw permutations with equal probability. So, how does uniform interleaver concept helps? Now we can come up with weight distribution averaged over all possible interlevers, and this helps us to compute the average weight spectrum of parallel concatenated codes. So again we are going to take a very simple example. This time we are going to use our favorite 7/4 Hamming codes as constituent encoders. So we are going to use a 7/4 Hamming code as a constituent encoder for turbo code, and both these constituent encoders use 7/4 Hamming code. So we are basically constructing a parallel concatenated block code. Now we know in a systematic form the weight enumerating function of Hamming code is given by this expression. There are 7 code words of weight 3, 7 code words of weight 4 and 1 code word of weight 7. So these are the non-zero code words in a systematic 7/4 Hamming code. Now the input redundancy weight enumerating function, this we have already defined when we talked about weight distribution of convolutional code. So the input redundancy weight enumerating function for this systematic Hamming code is given by this. So for our information sequence of weight 1, there exists 3 sequences which have parity weight 2 and 1 which has parity weight 3. For information sequence of weight 2, there are 3 sequences which have parity weight 1, 3 sequences which have parity weight 2, and so on. Now we can also find out the conditional weight enumerating function. So from this input redundancy weight enumerating function we can find out conditional weight enumerating function. So when input is 1, this is what we get. So the conditional weight enumerating function is given by, for input 1 is 3z squared plus z cube. Similarly, for input weight 2, the conditional weight enumerating function is given by this. So that's this. Similarly, for weight 3, the conditional weight enumerating function is 1 plus 3z, and for input weight 4, the conditional weight enumerating function is given by z cube. Now let us consider a parallel concatenation of these two Hamming code. Okay, so we have these two systematic Hamming codes C1, C2, whose conditional weight enumerating function is given by this and this, and we apply this concept of uniform interleaver to find out what is the conditional weight enumerating function of the parallel concatenated code. Now again, recall our encoder is something like this. So we have a systematic encoder, and then we have the information bit which is interleaved and fed to second encoder. This is the output. So the conditional weight enumerating function of the parallel concatenated code can be given by this. So for first encoder we have input weight W getting in, and this will give me the conditional weight enumerating function corresponding to input weight W. Similarly, for the second encoder, this will be the weight enumerating function for input W, and then averaging it out over all possible interlevers, I get this average conditional weight enumerating function given by this expression. So the nice thing about this uniform interleaver concept is it allows us to compute the average weight enumerating function of this parallel concatenated code, which is independent of the type of interleaver that we are using. Now similarly, we could define average input redundancy weight enumerating function is given by this expression. Now please note, these are straightforward extensions of the definitions that we have studied when we talked about weight enumerating function of convolutional code. We can define bit conditional weight enumerating function, average bit input redundancy weight enumerating function, average code word weight enumerating function, and average bit weight enumerating function. Now let us take an example to illustrate this. So we had this parallel concatenated code using 7-4 Hamming code. So input is length 4, and we get 3 parity bits from first encoder, we get 3 parity bits from the second encoder, and of course there are 4 systematic bits, so overall code word length is 10. So what we get is a 10-4 parallel concatenated block code, which are using identical constituent encoders, and this is your 7-4 Hamming code. Now using the expressions I have said before, we already know the conditional weight enumerating function of the constituent encoder. Now using this expression, I can compute the conditional weight enumerating function of the parallel concatenated block code. So these are the average weight enumerating. So corresponding to input 1, so you can see there are 2.23 on average sequences of parity weight 4, 1.5 sequences of parity weight 5, and 0.25 on an average sequences of parity weight 6. Similarly, we could find out for input weight 2, input weight 3, input weight 4. Now note the difference from the constituent encoders that we have studied. Here you can see these numbers, these coefficients are coming as non-integers, can come as non-integers, right? That's because we are averaging over all possible interlevers. And again, following the definition of input redundancy weight enumerating function, we can find out the input redundancy weight enumerating function, bit input redundancy weight enumerating function, which is given by these two expressions. And similarly, if we put W equal to Z is equal to X, we can get the weight enumerating function and the bit weight enumerating function, which is given by this. Now, points to be noted: we saw the coefficients of the code word weight enumerating functions are fractional. And why they are fractional? Because this is due to averaging effect over all interlevers. However, if you sum of all the coefficients, they add up to total number of non-zero code words. You can verify that if you add up this, okay, 0.25, 0.25 is 0.5, 7.5 is 8, 8 plus 6 is 14 plus 1 15. So you can see if you add them up, we get the total number of non-zero code words. And you can also see that average code word multiplicity has reduced. It's 0.25 when the input corresponding to input of 3, and it is 3 corresponds to input of 4. Similarly, bit multiplicity for input of 3 is 0.19 and it is 1.87 for input of length of weight 4. So if you compare this code multiplicity from the original code that we used, we were using 7-4 Hamming code, which had 7 code words of weight 3. Here you can see the average multiplicity is 0.25. So you can see the effect of interleaver on code multiplicity, and you can use this concept of uniform interleaver to compute your average weight enumerating function, average input output weight enumerating function, average bit conditional weight enumerating function. So all those quantities that we have defined in the context of weight enumerating function for convolutional code, you could do similar analysis for these parallel concatenated code using this idea of uniform interleaver. So with this, I am going to conclude the discussion on this distance properties of turbo codes. Thank you.